Okay, the recording has started. We are now underway. Anybody have any questions before I get into the normal class stuff? Questions about anything? Okay, I'll take that for a no. Okay. All right, well, let's talk about last time's quiz. See, the chat window just disappeared on me again. But luckily I have my other computer up, so we're okay. I'm gonna have to talk to the Zoom people about why does the chat window keep disappearing? Okay, anyway, so one of the quiz questions, the first quiz question was this one right here. It was, um, what is the mechanical advantage of this thing? All right, so anybody want to pipe in with an answer here? What is the mechanical advantage here? All right, so I see one person is saying 6, and the other person is saying 6.0, okay, which is exactly the reason why I chose the suggested answers that I did here. Okay, so John and Marshall, why do you suppose that the answer is not 6, but it's 6.0? Okay, so Sky is saying it's because of the 2.0. Yeah, so when we calculate the mechanical advantage here, we're going to take the distance to where we're exerting the effort force, divide by the distance to the resulting force. But look at the numbers. I got 2 sig figs here, and I've got 2 sig figs there. Now, if that had not been a 2.0, if that had just been a 2, it would have had only 1 sig fig. But the way I wrote it, it has 2 sig figs. So I got 2 sig figs divided by 2 sig figs. That means my answer needs to have 2 sig figs. That's the reason why. So yeah, I see the comment here that says, yeah, I forgot the sig figs are a thing. Sig figs are always a thing. Okay, so get used to it. And when you take chemistry next year, you will thank me for teaching you about sig figs, because I promise you, Coach Miller is going to hit it real hard. You've got to use sig figs for Coach Miller. And when you get in my physics class, I'm going to do the same thing. Sig figs are important. Okay, next question. What is the actual mechanical advantage of the lever shown in the previous problem? Okay, so I'll go back here. So here's the lever shown in the previous problem. All right, what do you guys think okay, so Sky is saying we need more information, and Sky is exactly right. Okay, and Sky, what is the information that we need? Okay, what information would we have to have in order to be able to calculate what the actual mechanical advantage is? How much the friction force affects it, right? Okay, so what we would have to do, let's go back up to here again. So if we're pushing right here on the lever, okay, we could measure how hard we're pushing. And then what we need to do is we need to measure how much force is coming out the other side of the machine. With friction, it's really hard to calculate it. So you just have to measure the two forces and then take the ratio of the two forces. Okay, without that, you can't know. But you can know the ideal mechanical advantage. If you look at the distances on either side, that will allow you to calculate the ideal mechanical advantage. All right, okay, so here we have a pulley. Okay, now if I were to ask you what the actual mechanical advantage is, well, I'd have to give you more information. But if all I need is the ideal mechanical advantage, you've got enough information. Okay, good. So I see that we got two answers here. Both of you are saying that the answer is -3, okay, which is good. Can somebody pipe up, why is the answer -3 and not +3? So let's see what you guys say about that. I need somebody to type something in here. Okay, all right, yeah, so the answer, you've got it exactly right there. So if I pull downward, the force, the resultant force is an upward force. They're opposite directions, okay? So that's why the negative. Now, I do need to warn you that many, many times people, when they calculate ideal mechanical advantages, they ignore the negative, okay? So don't be surprised, and I might even do this later on in today's presentation. I might look at a situation like this and tell you that the IMA is 3, even though really technically it's -3. But a lot of times people don't really care about the direction. They just care about the absolute value, okay? So even though the answer really is -3, don't be surprised if people say that it's 3. including me in a couple minutes. I'm going to do this. Okay. All right. Now here, this is the real test here. This is the problem that lets me know whether or not you actually understood everything. Okay, so I've got some machine, and I don't say what kind of a machine. Maybe it's a pulley, maybe it's a gear, maybe who knows? I don't care. The ideal mechanical advantage is 7.5. Okay, but when I try it in real life, I find that if I put an input force of 42 pounds, I only get an output force of 240, which is less than I should get. Anybody? Let's do this step by step here together. So if the machine was frictionless and the IMA is 7.5, so if I have an input force of 42, when you guys get out your calculators, what should the output force be if there's no friction? I need to see a couple answers here. So if the IMA is 7.5 and there's no friction, so the output force is in fact 7.5 times what the input force is. Okay, so I see a couple of you are saying 315. Actually, a lot of you are saying 315. Okay, good. All right, I agree with that. Okay, so now that we know that, okay, so we know that the output force ideally would be 315, but in fact it's only 240, so clearly friction is coming into play. So if I want to know what the efficiency of the machine is, what I do is I take the actual output force divided by what the ideal case would be, and that's going to give me a number less than 1. And we normally express efficiency in terms of percentages. So if I multiply it by 100 and then put a percent sign afterwards, okay, then I get the answer here. So the answer is 76% efficient. Okay, looks like you guys are on board with that. That's good. All right, so, all right, now the last question here. I've got a box. I'm pushing it up a ramp. It's a frictionless ramp to make things easier. Okay, so I want to know what is the heaviest box I could possibly push. I like to do this in steps. My first step would be to calculate what is the IMA of this machine, IMA, ideal mechanical advantage. So that would be the first step that I would do. I'm curious to know what you guys come up with. So let's just take it, just the first step only. What is the IMA of this ramp? I need a couple people there. Now remember, the way that you calculate the IMA is you just look at the distance, okay? So if I was not using the machine, I would just be able to lift the thing straight up, and 3 feet is all I would have to move the thing if I wasn't using the machine. But I am using a machine, so then 5 feet is what I need to do. Okay, good. So I'm seeing 1.7 is what you're doing. So we're taking the actual distance that I had to move my hand divided by the distance that it could have done had I not used the machine. So 5 divided by 3. All right, so Van is saying that it's 1.7. Okay, and I agree with him. Okay, and so now we can go on to step 2, which I see Sky has already done here. Okay, so if the strongest force that I could possibly exert is 480 newtons, then the output force would be 1.7 times that, which is 800. Okay, very good. Okay, all right. Now, when you guys take my physics class, either next year or the year after, I have a bunch of tools that I can measure how hard people can actually push, and we're going to do that every year. I do, and it's kind of fun to see. On average, most students, if they're pushing as strong as they possibly can, right around 500 newtons is what most students do. Now, there's a couple of really tough guys who can do 600 or even 700 newtons, but most people, about 500 newtons is typical for what they can get. So just a little trivia thing for you there. Okay, well, that's it for the quiz. Now, you did have a homework assignment, which was to finish reading chapter 3. So you should have all now done chapter 3. So let me pause for a minute and ask you if you have any questions about what you read. So I need to see something typed in there. I'm not going to move forward until somebody types something. So either type in no, you don't have any questions, or type in what your questions are. Do, 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 do. Okay, so one person saying no questions. Okay, all right, so a bunch of you are saying no questions. Okay, all right, well, in that case, I have some questions for you. Let me see if you actually did the reading that I wanted you to do and if you understood it. Okay, so in the chapter, they talked about 3 different types of levers: a first-class lever, a second-class lever, and a third-class lever. So let me see what you guys got when you read this. Okay, so can somebody tell me what's the difference between a first-class lever, a second-class lever, and a third-class lever? Now it's a little bit tricky. Typing it into the chat box is going to be a little hard to do. Anybody want to turn on their mic and try it? So if you hold down the space bar, you can just speak into the computer here. Anybody want to try telling us what's the difference? Nobody wants to volunteer? Did you guys actually do the reading? This was in the reading. If you did the reading, you should know this. Nobody wants to volunteer, huh? Oh, guys, what am I going to do with you? Oh, okay, somebody volunteered. Okay, good for you, Luke. Thank you, Luke. Okay, so Luke is saying that the difference is where he's saying the relative positions of the fulcrum to the resistance of the effort, which is exactly the way that a physicist would say it. So good for you, Luke. Okay, so let's look at some pictures here. Much easier to understand with the pictures. Okay, so with a first-class lever, the fulcrum is in between the effort and the resistance force. Okay. With a second class and a third class lever, the fulcrum is over here at the very end. Okay. So if you look at the picture, you say, well, a second class lever looks an awful lot like a third class lever. What's the difference there? It's where you put the effort. With the second class lever, you're putting the effort way out here at the far end, and whatever it is that you're lifting is in the middle. And with a third class lever, you're actually pushing in the middle, and the thing you're trying to lift is on the outside. So the best way to think about this is with some actual pictures. Okay, so a first class lever is the kind that, so lifting or lowering, yeah, David, it could be either. Okay, it could be either. Okay, so first class lever is like the teeter-totter that you guys are all familiar with. That's what, when people think of a lever, they use first class lever is generally what people think of. A second class lever would be something like this wheelbarrow or a bottle opener. A bottle opener is also another example. Okay, so with the wheelbarrow, you see, okay, hang on a sec. Okay, all right. So this point right here, that's where the fulcrum would be. Okay, you exert the force out here at the end of the handle, and then the heavy thing that you're trying to lift is in here. Okay, so wheelbarrow is a perfect example of a second class lever. Okay, and then the third class lever, well, that one is this picture here that you see that looks kind of like a skeleton's arm. Well, that's exactly what it is. This is the human body. Your arm is actually a great example of a third class lever. Let me enlarge that here so that you can see it a little bit better. Okay, so the human muscle, the bicep in your arm, is actually an incredibly strong muscle. It can exert a tremendous amount of force, but it can't exert that force over a very big distance. When the human bicep contracts, it only contracts a little bit. Very strong, but only a small distance. So if you got something over here that's pretty heavy and you want to lift it, and you want to lift it a big distance, the muscle, I mean, it certainly has more than enough strength, okay, but it doesn't have the distance that's needed. So what we do is it's hooked up like a third class lever here, right? So so this is how it works. So I want somebody to do a little math here, literally just bone, huh? Okay, all right, yeah, so yeah, the forearm does come into play, I agree with that. But let's just keep things simple. All right, so with this lever here, I want you guys to tell me how much force would the bicep have to exert in order to lift a 30-pound tool bag if we have the dimensions here. So the bicep is acting at a point that's 2 inches away from the pivot point. the tool bag is way out at 12 inches away from the pivot point. So how much force is the bicep going to have to exert in order to do this? This is the kind of problem you might see on today's quiz, wink, wink, nudge, nudge. I'm not seeing any answers yet. Okay, so Van's saying 5 pounds. So what do the rest of you think? I need to see a few more answers here. Okay, Luke is saying 180. Okay, so it looks like we're kind of evenly split. I see some people are saying 180 pounds, some people are saying 5 pounds. Okay, so with this third class lever, I want you to recognize that because the effort force is closer to the pivot point than the resistance force, okay, this machine here is not going to increase the force. The output force here is not going to be less than the input force, or it's not going to be greater than the input force, the way that the machines have that we've been talking about up until now. The output force is actually going to be less, okay? So the effort force is going to have to be more than 30, not less than 30. So those of you that said 5, okay, we can rule that out really quickly. Okay, so we've got several people who are saying here that it's 180. All right, so let's see how they came up with that. So the first thing I want to do is I want to calculate what's the IMA of this machine. All right, so the IMA, if I look at the distance, so this distance divided by that distance, that's going to tell me the IMA. So 2 divided by 12, okay, is 1/6, okay? Now that doesn't mean that the effort force is going to be 1/6 of the resultant. What it means is the resultant is going to be 1/6 of the effort. So that means the effort force is going to have to be 6 times greater. So if I want to lift a weight here that's 30 pounds, the force that bicep is going to have to exert has to be 6 times greater than 30. So it has to be 180 pounds. That's a strong arm. I agree with you, Sky. The bicep is a way stronger muscle than people realize, okay? It just can't exert that force over a very big distance, but that's okay because it's so strong. All right, so everybody okay with this? Any questions on this before I move on? So now you understand the difference between first class lever, second class lever, and third class lever, right? And by the way, you guys, you should have got this from the reading, okay? When I ask you to read the chapter, I want you to read it and understand it. Don't just let your eyes move across the page and you say, okay, I've read it, but you didn't actually understand. So those of you that didn't get this, when I asked a few minutes ago, I said, do you have any questions? This is the kind of question that I was hoping that you would ask. I was hoping you were going to say, hey, the book talked about first, second, and third class levers, but I don't understand that. Okay, so finger wag for you guys. All right. Okay, let's move on to a couple other things here. All right, so pulleys, we talked about those before. So if I were to ask you a quiz question where I said, what is the IMA of this pulley right here? What would you guys say? Let's pause. What do you think the IMA of this pulley would be? So I see 3 ropes here. Does that mean the IMA is 3? The IMA is 1. Okay, I see that. Let's see a few other answers. Okay, the IMA, somebody here is suggesting 2, but with a question mark. Okay, -1. Okay, so here's the trick for pulleys. So remember this and you will never go wrong. Okay, so the first thing you need to do is you need to look at where is the weight that we're trying to lift. So this is the weight that we're trying to lift. Okay, so then what we do is we draw a box around the pulley that is connected to the weight. Okay, so like this. Okay, so in our mind here, we've drawn this box. Okay, and we see that we've got one connection down at the bottom. So think of this like a rope here. In this case, it's a solid bar, but it could just as well be a rope. So we got one rope going down. We got 2 ropes going up. Okay, so when I pull on the rope over here, I put a certain amount of tension in the rope. So tension is just another word for a stretching force. So let's suppose that I put 100 pounds. Well, that's a lot. Let's say 10 pounds. Let's suppose that I pull on this rope with 10 pounds of force. So I have put 10 pounds of tension in the rope. And now if these pulleys are all frictionless, that means that the tension here is going to be the same as the tension here, which is going to be the same as the tension here. Okay, so everywhere in the rope here, this rope is trying to be pulled apart, and the force that's doing that is a 10-pound force. Okay, assuming that I'm pulling with 10 pounds here. So that means I've got a 10-pound force here pulling upward. I've got a 10-pound force here pulling downward, or also pulling upward. Now, right here, I've got a 10-pound force downward and 10 pounds pound force downward. But I don't care about these forces up here. I have drawn this box here specifically to focus your attention on the part that's important. So our job here, the reason we have this pulley is we want to lift this weight. Okay, so what we do is we look at the part of the pulley that's connected to the weight. We draw a box around it, a dotted box, and we say, okay, so if I'm pulling with 10 pounds here, that means I've got 10 pounds in this rope and 10 pounds of force in this rope, so I got 20 pounds going up here, but I've only got one rope going down. So this one rope going down must be equal to the two ropes going up. So that means that the force here must be a 20-pound force. Okay, so the IMA of this pulley is going to be 2. Now, actually, it's -2. Like, remember, we talked a few minutes ago. I warned you I was going to do this. Okay, technically, the fully correct answer is that the IMA is a -2. But people usually leave off the minus sign unless it's important. I mean, there are instances where it is important, but if it's not important, people usually just leave off the minus sign and just say the IMA is 2. Okay. I'm gonna, if I don't see any questions, I'm gonna assume that we're good with this. Okay, so in the quiz today, I might put a couple different types of pulleys in here and ask you what the IMA is. I hope that you guys will do well on that. Okay, so I'm glad to see that you agree that it makes sense. Okay, now here's another type of pulley or another type of machine that they talked about in the book, and I hope you guys actually understood what you read. I'm beginning to worry. Okay, so what we have here is a wedge. So we're pushing down on the wedge, and the wedge is going to push sideways. So it's going to convert our downward force into a sideways force. Okay, so if all we care about is the absolute value of the force multiplier, so I would want to know what the force multiplier is. Now, in order to answer the question what the force multiplier is, what the IMA is, we would need to know what the dimensions are. Okay, so let's start off, let's keep it really simple. Let's say that instead of using this wedge right here, let's say we just use this wedge right here. So it's a nice right triangle. We like right triangles, they're easy. Okay, so if I were to tell you that this distance A was 4 whatevers, 4 centimeters, 4 inches, I don't care. Let's say inches just because most people are more familiar with that. So I've got a wedge here that's 4 inches in the dimension where A is shown, and it's 12 inches in the dimension where B is shown. So if I were to take this wedge and I put it in there and I shove it downward, okay, so my force is going to get multiplied. So my downward force is going to get converted into a horizontal force, and my downward force is going to get multiplied. Okay, so if there was no friction, then the way that I find the IMA is that I take whatever is the distance that I would push the wedge, so that would be 12, divided by whatever distance the wedge is going to end up pushing on these two blocks here. So if I take the ratio of the distances, that'll tell me the IMA. So the IMA here is going to be 12 over 4, which is 3. Okay, so it's going to multiply my force by a factor of 3. And it's also going to redirect the force from being a vertical force being a horizontal force. All right, so wedge helps putting in windows. Okay, I've never installed a window. That's good to know. Yeah, I can see how that wedge would help putting in a window. That makes a lot of sense. Okay, so now the wedge that they show here is not a right triangle like that. It's this other V-shaped thing. So okay, so let's say that I take my wedge here and I get 2 wedges and I flip them, I put them side by side like this, okay? So what I've done is I now have a V-shaped wedge that's now twice as wide as it was before. Instead of being 4 inches, it's now 8 inches across here, okay? But the vertical still is 12, okay? So what does that do to my IMA? That actually reduces my IMA. My IMA used to be 3. Now my IMA is only 1.5. okay, because the formula is still the same. The formula is whatever distance do you, your hand, what distance does your hand move, which in this case is it moves 12, divided by whatever distance the machine moves, okay? So that's, in this case, it's going to be 8. So my IMA, which used to be 3, my IMA now has gone down to only 1.5. Okay. I hope that this is clear. Okay, so these are the kinds of things I'm going to ask you on the quiz, so be prepared for that. All right. Now also in the book they talked about gears. Now we've also done a little bit of work with gears, and we're going to come back and revisit it. Now in the book they talked about the difference between a gear and a sprocket, and I hope you guys all understood that. Okay, so if you're taking a gear and you're connecting it directly to another gear, or if you're connecting it to this thing here, which by the way is called a rack. Okay, if you have a gear that if you have a straight piece of metal with gear-like teeth cut into it, that's called a rack. Okay, so in this situation we call it a gear. Over here, what you see here technically is a gear, but it's a special kind of gear. It's a gear where the teeth have been shaved down so that they fit very well with the chain. Okay, so we give this a different name. I mean, technically it is a gear, so it would not be incorrect to call it a gear. But just to avoid confusion, we call it a sprocket. So a gear that's designed to interface with a chain is called a sprocket, whereas otherwise it's just called a regular old gear. Okay, so that might be useful information in a quiz or whatnot, who knows? Okay. Now, if you have a gear that's designed to interface with a rack here, we call it a pinion gear. And a pinion gear just looks like any old regular gear, so we just give it a name, okay? And have any of you guys heard about rack and pinion steering? Any of you guys really into cars? Back when I was your age, when you turned the steering wheel, the way that force got transmitted to the wheels to turn the wheels was kind of a complicated arrangement. And it worked okay, but you know the reliability could have been better. And then some car engineers, they came up with the idea, well, tell you what, let's take this gear right here, and there's going to be a shaft going through it, and we'll attach that shaft to the steering wheel. So when you turn the steering wheel, it turns the pinion gear, which then turns the rack, and then the rack is attached to the wheels. And so when I was your age, rack and pinion steering was a pretty new idea, and not all cars had them. But nowadays it's pretty standard. Most cars now have rack and pinion steering. There's a few out there that don't, but most of them do, because it's a very simple, it's a good design. Okay, let's move on. Okay, now remember when we were talking about the gear creations that you guys came up with, Sky went over and above the Call of Duty, and he came out with this super duper gear device of his. And remember how you turn the crank here and it turns these wheels here, but this gear interfaced with this gear. And they're, you know, normally gears are, you know, in the same plane, but in this case, it's rotated. So I've got a gear in one plane and the other gear is rotated 90 degrees from this, okay? So if you look at how the small gear here is interacting with the big gear, you hopefully will see something interesting. And in fact, let me zoom in on it so that you can see it even more clearly. So here's the small gear. Here's where it interfaces with the big gear. So you can see that it will work. Okay, the small gear will be able to drive the big gear, but it's not going to be as good a design as we would like, because you see this part of the tooth, it's not touching anything over here. All of the force from the small gear is all being exerted right in this space right here. This part of the gear might as well not even be there. It's not touching anything. And same thing with the small gear. You know, this part, the left side of the tooth here, isn't doing anything. So all of our forces are acting right here. And it'll work. But over time, what's going to happen is that our teeth are going to start wearing funny. Okay, we're going to get a lot of wear right here, and we're going to get no wear right here, and our teeth are going to get deformed, and over time, a reliability problem is going to arise. Now, there is a solution to this. What you do, anybody want to recommend a solution? Anybody know of a special type of gear that is designed specifically for this application? All right, I don't see anybody typing anything in, so I'll go ahead and type. Oh, good. All right, Luke, good for you. Yes, there's a special kind of gear called a bevel gear. And this is what a bevel gear looks like. Okay, well, this is what two bevel gears look like. So what you'll see here is that the teeth are cut at an angle, and we call that beveling. When you cut something at an angle like that, that's called beveling the thing. So you can see here where this gear, all of the teeth, the whole part of the tooth here is interfacing with the whole part of the tooth here. So if you want to do something like Sky did in his creation a couple weeks ago, you don't want to use normal gears. You want to use a special kind of gear called a bevel gear. That's a big brain. Okay, I guess kind of, sort of. Okay, I won't argue with that. Okay, so bevel gears are not the only kind of special gears. There are a lot of variations on how you can do gears if you want. Okay, so a normal gear, the kind of gear that you and I have been thinking about when we said the word gear up until now, that would be called a spur gear. That's your plain old vanilla ordinary gear. But you can see that there are many different types of gears here. Okay, so we got the bevel gear. This is the straight bevel gear. But you can see that if you curve the teeth here, like on the miter gear and the spiral bevel gear, what they've done is they've curved the teeth. So engineers have figured out that if you curve the teeth, it works a little bit better. The way that the forces of one tooth on the other tooth interact with each other, it turns out that you get a little bit better reliability. The wear and tear on the gears is a little bit better. So I mean, you don't have to. I mean, a regular straight bevel gear is good. So Sky is saying that the worm gear is cool. I agree. I like worm gears. I think they're pretty cool. So take a look at the worm gear here. Okay, so what you've got is you've got a regular old spur gear. The gear on the bottom is just a normal vanilla regular spur gear, nothing special about that. But on the top here, we take what is basically a screw or a bolt, if you want to think of it that way. Okay, and so we've taken this cylinder on the top here and we've cut these screw-like teeth into it, and they're the right shape, so they interface with the spur gear below it. So when you spin the shaft here, it ends up turning the gear below it. So yeah, worm gears are actually very, very cool. Okay. Down here we see the rack and pinion, which we've already talked about. Up here, the helical gear is basically a spur gear where they're turned at an angle. It's kind of like the miter gear versus the straight bevel gear. Okay, only it's for regular spur gears. A double helical gear. To be honest, I don't know the reason why you'd want to use this herringbone type gear, but obviously there must be some reason for it, or people wouldn't do it. Okay, so Sky wants to know, why would you want to use a helical as opposed to a spur gear? So as I was talking, Sky was obviously typing. I got to be honest here, Sky. I'm not sure what the advantages are of a helical gear over a spur gear. If any of you guys want to do a little research and let us know on Friday when we meet on Friday, that would be good. I might even give a little extra credit for that. If somebody could write up a report on why would a helical gear be preferable to a spur gear. It looks cooler. Okay, I agree with you, Van. It definitely looks cooler, but is there some functional reason for it? Okay, so now let's go back to the gears that you guys designed a while back. Okay, so all of you designed a gear train. So what you have now is a machine, and this is what we call a compound machine because we've actually got different parts here. So we're going to have an IMA from when the first two gears interact with each other. That's going to give us one IMA, and then when these second ones interact, that's going to give us another IMA. So when all four of them act together, the two IMAs get multiplied together. Okay, so one of the things that I expect you guys to do, and when we take the midterm exam for this unit, I guarantee there's going to be questions like this on the midterm exam. What is the IMA of the gear train? Now, when we did this before, we weren't worried about the force multiplier. We were focused in on the spin multiplier, which is basically a distance multiplier. So what we did when we did this before was said, okay, this gear here has 40 teeth, and this gear here that it's interacting with only has 8 teeth. Okay, so if we turn the big gear 1 full revolution, the small gear is going to turn 5 full revolutions, because whatever 40 divided by 8 is. Okay, so that's okay. Okay, so let me get here. Okay, so 40 divided by 8 here, which by the way, yeah, that's 5. Okay, good. I was getting a little worried about my math here. Okay, so the small gear is going to spin 5 times for every 1 time that the big gear spins. Okay, so then we said, well, the spin multiplier is 5. But the force is the exact opposite of that, or actually inverse is a better word to use, reciprocal. Okay, so if the small gear spins 5 times for every 1 time that the big gear spins, okay, that means that the torque on this second shaft here is going to be 1/5 of the torque on the original shaft. Okay, so if the spin multiplier is bigger than 1, that means the force multiplier, or in this case, the torque multiplier, is going to be less than 1. Okay, so I hope you guys got that. Okay, now let's look at the other one down here. Okay, so again, this is the driving gear, and this over here is the driven gear. So if the driving gear is bigger than the driven gear, that means that the driven gear is going to spin more than the driving gear. So the spin multiplier is going to be a number greater than 1, but the force multiplier is going to be the reciprocal of that. So it's going to be less than 1. Okay, so if we put them all together here, so the IMA is 1/5 or 0.2, and over here the IMA is 16 over 24, which is 2/3. Okay, now the total IMA is not going to be the sum of the two. The total IMA is going to be the product of the two. So we're going to multiply them together. So the total IMA, or in this case, now I'm going to call it a torque multiplier because it's not the spin multiplier now. The total IMA of this machine here is going to be 0.13. Okay. Now this is not counting the handle. The handle is acting like a lever. So if I have a handle, then my force multiplier is going to be even more. But I don't want to confuse things right now. So let's pretend that we don't have the drive handle there. So pretend we're just putting this onto, let's say we've got an electric motor. So electric motors, they only spin. So they put out torque. So if I take this shaft right here, if I connect that to an electric motor, okay, and it puts out a certain amount of torque, then the torque on the output shaft here is only going to be 13% of what my input torque was. Okay, so it's not multiplying my force. It's actually let me rephrase that. It's not increasing the torque, it's decreasing the torque. But what do I get in exchange? Well, this flag over here is going to be spinning like crazy. Okay, because every 1 time my input shaft spins, my output shaft here is going to spin 7.5 times. Okay, so if I want the output shaft to spin really fast, this is what I want to do. Now, what if I really need more torque? Let's say I've got some application where I need more torque than my machine can put out. Okay, well, in that case, instead of using this as the drive shaft, let's have this be the drive shaft. Okay, so I'm putting the handle over here to illustrate that I want this now to be the drive shaft. So this is where I'm going to connect my electric motor to. So now everything gets flipped. Okay, my IMA now, which used to be 2/3, now becomes 3/2. So this shaft right here is going to have 1.5 times more torque than my drive shaft. And over here, my IMA used to be 1/5, now it's 5. So that means the torque on this shaft is going to be 5 times greater than whatever the torque on this shaft was. Okay, so if you multiply 1.5 times 5, you get 7.5. Okay, so this is the kind of thing I expect you guys to be able to do. So Sky is saying it gets complicated. Yeah, it might look a little complicated, but if you just take it one at a time. So just look at this gear pair. Look at that first and figure out what is the IMA for that gear pair. And then take the next gear pair and ask yourself, what is the IMA for that one? Okay, and then once you know the IMAs, then you multiply them. Okay, all right. Okay, I don't see any more questions or comments, so I'll move on. Okay, you guys have heard of a Rube Goldberg machine? So Sky, if you thought what we did before was complicated, well, yeah, wait till you get to this, okay? Rube Goldberg machines are things that are purposely complicated, okay? You've got a really simple task. All you want to do is you want to push this stapler, okay? So you could just take your hand and push the stapler, but where's the fun in that, okay? So Rube Goldberg is a guy who was a cartoonist way back a long time ago, like 100 years ago, okay? And he came up with all these incredibly whimsical, fanciful inventions where he came up with a crazy complicated way to do a very simple task. Okay, as David likes to call it, time consuming while in quarantine. Yes. Yeah, Rube Goldberg machines are definitely fun. And so if you think they're fun, then you're gonna like this. Our midterm exam, which by the way, we're not ready to take our midterm exam yet. It's gonna be a while before we take our midterm exam, but the midterm exam is going to be for you guys to design and build a Rube Goldberg machine. That is going to be the final test for this unit. So you like that? Is that the kind of test you guys like? Okay, good. I'm glad to see it makes you happy. You're going to like it. Now there's going to be some rules that you have to follow, and I'm not ready to release the rules yet. So don't worry, it's going to be a while before we take it, but you guys are going to have to, have certain types of elements inside your machines. You know, like I'm going to say, well, you have to use a pulley together with a gear train, together with a lever, together with something. I haven't yet decided the rules, but that's what it's going to be. So in this particular case, I trust you guys can look at it and figure out how it works, okay? So what happens is when the alarm clock goes off, so let's say you want to staple something, but you don't want to staple it right now. You want to staple it an hour from now or 2 hours from now, right? Okay, so you set the alarm clock for whatever time it is that you want the thing to be stapled. When the alarm clock vibrates, it causes this little ball here to, the table vibrates, so it causes the ball to fall off into the wheel. And when the wheel turns, it knocks the cup over. And then there's some stuff in the cup that rolls into this lower cup down here. When you get the weight in the lower cup, it causes the scissors to close, which cuts the string that's holding the boot up, and the boot then comes down on the stapler machine. So this is a classic example of a Rube Goldberg machine. And so something like this is what I want you to design and build. And I will give you time to do that. The reason I tell you about it now is I want you to start thinking in the back of your mind, even though it's not due for quite a while. I want you to start thinking now, what might you do for your Rube Goldberg machine? I'm going to give you a lot of leeway with this. I mean, I'm not going to tell you what the final goal of your Rube Goldberg machine needs to be, but I am going to say that one of your elements needs to be a such and such machine, and another one of your elements needs to be a different type of such and such machine. And I am going to ask you to calculate the IMA for each of these elements that are in here. Okay, so start thinking about it now. Okay, so your homework for tonight is to go on YouTube or some other channel. I realize YouTube's not the only place out there that has cool videos, but it is far and away the most popular. I want you to go on YouTube and find some interesting Rube Goldberg machines. Now let me show you an example that I found on YouTube. And in fact, this is a TV commercial that they used to play several years ago. Honda makes cars, and Honda has a reputation for high reliability. Honda cars, they usually work really well. Okay, so what the people at Honda did, which I really loved, was they took one of their Honda cars, they took it apart, and they took all of the pieces. So everything that you're going to see in this video that I'm going to play in just a minute, okay, everything that you're going to see here is a part from a Honda car, but it's a part that has been put together in a really crazy way, okay, to accomplish basically a Rube Goldberg machine. Okay. So get ready for 2 frames per second, guys. Yeah, hey, that's Zoom. What can I say? All right, so here goes. Let's see how the Honda people came up with their Rube Goldberg machine. Okay, so here we go. What you're seeing right now, that's the muffler system. And what those are called cams. There's parts of the engine, and it's sitting on the car hood. Okay, so that's the air filter. These wheels are interesting. Now, how do you suppose they got the wheels to roll uphill? That's interesting. I want to talk about that in a minute. Okay, all right. Okay, that's a windshield wiper. Okay, that's some oil. Okay, those are various bearings. That's part of the engine. That's the car battery now. More engine parts. Okay, that's the fan for the radiator. Okay, various miscellaneous engine parts. That's a muffler that you're seeing right there. Okay, more wheels and gadgets. Various engine parts. If you look inside an engine, you'd find those are the parts. Okay, rolling down the window, the electric window. Various door handles. There's a car battery hooked up to the windshield wiper fluids. Okay, the sensor turned on windshield wipers. Various windows on a little interesting assembly. We're almost done here. Okay, the spring from the tire assembly, another battery. Turned on the sound system here. And we push the remote control on the key, which closes the door to another Honda car.
Isn't it nice when things just work?
Yeah. Okay, so I hope you guys could hear the sound there. So at the very end, the announcer says, "Isn't it nice when things just work?" Right? So obviously the idea they're trying to drive home is that Honda cars, you know, even the little tiny details, they all work really well. Okay. Okay, so that is similar to what I want you guys to do as your homework assignment. So you don't have to calculate any IMAs. You don't have to, do anything. All you have to do is look on YouTube or somewhere else and find a cool video of a Rube Goldberg machine that you like, and then send me the link to that video. All right. So that sounds like a pretty good thing. Now, let's see if we got time. No, we're running short on time. So one thing I'd like you guys to think about is, remember the tires, how the tires were rolling uphill? How do you suppose they did that? How do you get something to roll uphill? So Sky is suggesting it had a lot of momentum. Van is onto it, weight distribution. What they did was they took some heavy weights and they put it inside the wheel. I should have brought so imagine you've got a wheel here. If you put something inside the wheel, something really, really heavy over on this one side, it could make it so that the wheel would roll up the hill. A futuristic anti-gravity device, yeah. Okay, so let's get on with this. Okay, so as I said, your homework assignment is to find a cool video on YouTube or wherever or where else of a Rube Goldberg machine. Upload the link to Canvas. Now I don't yet have Canvas set up to accept links yet, but about an hour or 2 or 3 hours from now, once I get the recording back of this video that we're doing right now and the daily quiz, I will also post a place on Canvas where you can upload links. And of course, don't forget to take the daily quiz. Now, I don't consider the daily quiz to be homework. The last couple daily quizzes have been a little bit harder than usual. I'm going to try and make today's daily quiz a little bit easier. There will be 1 or maybe 2 questions where you'll have to calculate IMAs. But the rest of them, as long as you watch the video, you should be fine. Okay. So we're coming up on a little bit less than an hour. So I like to keep these classes under an hour. Oh, secret word. Yeah. Okay, good. I'm glad you reminded me. Secret word. Okay, so you want to suggest a secret word? I had a Sharpie here, so that I don't know what happened to my Sharpie. Okay, mousetrap, plume, glurb. Okay. Well, you know, mousetrap. Because you guys have played the game Mousetrap, right? The game Mousetrap is the perfect example of a Rube Goldberg machine. Perfect example. Okay, so I think that's an appropriate secret word for today. Okay, I don't know if can you guys even see that? Okay, so mousetrap is the secret word for the day, or I guess secret phrase, seeing as how, yes, I agree with you, Sky, that's 2 words. Okay, so we'll call it the secret phrase for today. Okay, so are there any questions? Going once, going twice. So